Okay, so we are busy interpreting beta, and what we did was we let p is equal to m, and then we find that the Green's function becomes 1 over m squared times a function of gp, and it's natural to interpret the series expansion of that function as the perturbation series, and this is indeed the correct interpretation. Now take a look. The same function, which we've just said is the perturbation series, that appears at the scale p is equal to m also appears at the general scale in the solution that we wrote down. The difference is that we don't use GP. In fact, we use G bar. So what is the interpretation of G bar? G bar is the effective coupling at the scale P. So at the scale P, you don't use the physical coupling GP, you use the coupling G bar. So now the coupling constant is no longer a constant, it's an effective coupling constant. And as you flow down in energy, the value of the coupling constant changes. The thing that tells us how the value of the coupling constant changes is the beta function. So now we've learned what the beta function means. The anomalous dimension we interpreted, and we learned that the anomalous dimension is related to the wave function in normalization. And the anomalous dimension tells us how the field strength changes as we flow to low energies. The beta function tells us how the coupling constant changes as we flow to low energies. And G bar is the coupling constant at the scale P. So this is the running coupling. G bar is the running coupling. Let's work out the running coupling for our 5-4 theory, for which we have already worked out the beta function. Beta was 72, the physical coupling squared divided by 4 pi squared. So to work out the running coupling, we need to solve the differential equation. dg bar d log p over m is equal to the beta function. And the beta function is just 72, the physical coupling squared, divided by 4 pi squared. And this is a particularly easy differential equation to solve. I'm sure you've solved many like this before. So we take dg bar over, we should put in the beta function as a function of g bar. So that should be g bar squared. Good. So we'll have g bar divided by g bar squared. So I've kept the dg bar on the left-hand side, and I've taken all of the g bar dependence onto the left-hand side. Then I'm taking, so I'll have 72 4 pi squared left, and I will take the dependence on d log p over m over, good, d log p over m. And now this is very easy to integrate. So dg over g bar squared integrates to minus 1 over g bar is equal to, I'll have 72 4 pi squared. We will have a log p over m, because that's what d log p over m integrates to. And of course, there's always an arbitrary integration constant, which I've just called c. And to figure out what c is, we should evaluate things at p is equal to m, where g bar is gp. So at p is equal to m, at p is equal to m, we find minus 1 over the physical coupling is equal to, now plugging in p is equal to m, we get log m over m, which is the log of 1. So that term disappears. This is just equal to c. So we now know what c is. I'm going to do a trivial piece of algebra to rearrange this. So here is g bar is equal to, it's the physical coupling over 1 minus 72 over 4 pi squared, the physical coupling, times by the log of P over M. Good. Now, of course, this is not the exact running coupling. It's the running coupling when we've got a one-loop approximation to the beta function, okay? But let's see how G bar behaves. So we can plot G bar versus P. At P is equal to M, the value of the coupling is set by the physical coupling. So that's where we start off. As we flow to scales less than M, P over M will be less than 1, so the log of P over M is negative. Multiplied by the minus sign up front means we have a positive number, so we have GP over 1 plus a positive number. So GP is getting smaller. As P flows towards 0, log P over M is a very large negative number, and in fact, G bar starts to flow towards 0. It gets logarithmically smaller, and in fact, it flows towards 0 at the origin. So the coupling would actually hit the value of 0, according to this function, at the origin. So we can say it flows to 0. Okay, that's as you flow to lower scales. Now, I want you to recall something. Recall that from the free field fixed point classification, remember that this operator GP multiplied phi to the 4. And from this, we classified GP as marginal. Now, this was one of those cases where we said, because GP is marginal, that means that the third step of the renormalization group, when we scale the momenta, it doesn't cause the coupling to change at all. In this case, quantum corrections can't be neglected. They must be taken into account. And what we've learned is quantum corrections, so loop corrections, make GP irrelevant, because now we find that it does flow to 0 at low energies. Well, we have a name for this. We say that G is marginally irrelevant. So when you see people talking about a coupling that is marginally irrelevant, they mean in the free field fixed point classification, the operator would have been marginal, but when you add quantum corrections, it becomes irrelevant. So now we know exactly how to interpret the Kalan-Samanzik equation. Beta tells us how the coupling changes under the RG flow. And the anomalous dimension gamma tells us how the field strength changes under the RG flow. Okay. And well, you've seen the argument for this. That's what we've actually developed by using our solution of the Kalan-Samanzik equation. Very good. So in actual fact, can you see that for phi-4 theory, at low energies, you would trust perturbation theory. So at low energies, it is perturbative. It's weakly coupled, okay? And that means that you can use perturbation theory. You can study the perturbative limit of the theory, which is great. At high energies, of course, you'll be in trouble because at some point the coupling is going to become large and you wouldn't really know what happens to the physics. Okay, very good. So that actually brings us to the end of what I wanted to say about the Kalan-Samanzik equation. I think that now you should understand Kalan-Samanzik. So you've got an idea now how to do certain calculations in quantum field theory. One of the central things about quantum field theory that we had to understand were these infinities that appeared that led us to develop this theory of renormalization. And we've now discussed Wilson's point of view and the Kalan-Samanzik equation. And I think you should have a very good physical intuition about how renormalization works. So the only thing left for the course is to describe the exercises. In the exercises, there's a few things that I wanted you to do. So the first exercise, I want you to consider a beta function that is negative, okay? And that's different to the example that we considered. You can see our beta function was 72 GP squared over 4 pi squared. So we studied an example of a beta function that is positive. For any beta function that is positive, the theory becomes weakly coupled in the infrared. So this would be the infrared limit of the theory. This would be the UV limit, and it's perturbative in the infrared. When beta is less than 0, you can go through exactly the same calculation. So this will be G bar. This will be the scale P. And what is nice now is that you get the effective coupling actually behaves like this. So in the UV, you are weakly coupled. So in the UV, you would be weakly coupled. And in the infrared, you are strong. You're in the region of strong coupling. Okay? So that's how that works. This is a very interesting theory because, in fact, quantum chromodynamics, QCD, is exactly a theory with a negative beta function. And in QCD, it's strongly coupled in the infrared. This is why it's so difficult to demonstrate confinement and chiral symmetry breaking and to derive nuclear physics from an underlying microscopic QCD Lagrangian. It's because the theory becomes very strongly coupled in the infrared. And so far, we don't have good techniques to develop the dynamics of strongly coupled field theories. A very promising approach is the 1 over n expansion for quantum chromodynamics, and a very promising recent progress in the direction of the 1 over n expansion is the ADS-CFT correspondence. So one of the major motivations of the ADS-CFT correspondence is precisely to understand strongly coupled field theories, quantum field theories, and in particular QCD at low energies. This theory we say is UV free, and that's just because the theory becomes free at high energies. This statement that the energy becomes free at high energies, it's basically just a bunch of gluons and quarks that are weakly interacting. This is called asymptotic. So it only happens when you really get up there to very high energies, and it sets in very slowly logarithmically. It's called asymptotic freedom. And this won a Nobel Prize, okay? And the recipients of the Nobel Prize was Gross, Wilczek, and Politzer. Now, this might be inspiring for you to know, but Frank Wilczek and David Politzer were both PhD students when they did this work. So you might be a PhD student watching this YouTube lecture. They won a Nobel Prize in their PhD, so I challenge you. Can you do the same? So aim high. Let's see if you can get a PhD in, if you can get a Nobel Prize during your PhD. Okay, next, let's take a look at the next exercise. In the next exercise, I've asked you to study two scalar fields that are interacting. Okay, so if you go through that, it's a completely straightforward exercise. You just use renormalized perturbation theory, work out the Feynman rules, calculate as many correlation functions as you need to determine there'll be two beta functions now and their anomalous dimensions for this theory. What you will find, so let me give you a little hint, the anomalous dimensions for both of the fields vanish. And this is very generally a property of scalar fields that have a 5-4 interaction, even if not all of the species at the vertex are the same. So you should find that the anomalous dimensions vanish, so the field strength is independent of the scale. And you should be able to calculate the beta functions. So calculate the beta functions. What you will find as you flow to low energy, there is an enhanced symmetry. So look out for that. So as you flow to low energies, you should find that the symmetry in the theory is enhanced. So that's a nice problem for you to spend some time with and to try to really understand. Great. Okay, guys, that brings us to the end of the course. So I hope you've enjoyed it. And quite possibly, we will have another course, maybe one on quantum field theory, sorry, on conformal field theory, or maybe we'll have one on quantum field theory dealing with many of the things that we haven't covered, like gauge symmetry, vector fields, adding fermions, so matter, even calculating scattering amplitudes. So there's many, many other things that we could consider. And let's see what we want to do for our next course.